All right, so we're going to complete the CER2. We are looking for the electrostatic force and distance between the two objects. So this time we're going to keep the charges the same. We're going to change the distance. And we're also going to try to use the same charges. So we're going to use positive, positive, or negative, negative. And we're going to just change the distance. So using the same website that we were using from number 1, we have here two ions. One is stationary. So this is the stationary ion. Oops. We're going to pause that. Okay, so we have two charges. This is a positive one, and we have a negative one. So we're going to make them both the same. We're going to turn this into a negative or a positive one. So we are going to increase the charge. So now they're both positive 1. They're both the same charge. Notice that our distance was still left at 2.5 angstroms. We're going to change the distance. So expect to see some changes here. Okay, and so what we're going to do is take this and move it. And then what happened to our force of repulsion? Let's try that again. Okay, so first what we have here is two ions that have both positive charge, and their force is going to be 3.7 times 10 to the negative 9. So let's see if we can write that somewhere. So we had 3, that's not what I wanted to do. All right, so if you take a look over here in the graph where there's a force and a distance, well, you can see that there are two plotted points here. There is a distance of 2.5 angstroms and an electrostatic force. And then there is one here that we did earlier. So let's go ahead and see what that looks like when we bring it further apart. So we're going to go to 5.78 angstroms, which is almost like almost 6, and it is less. You can see that there's arrows that are less. All right, so now let's go ahead and bring the ions closer together than 2.5. So if we bring this ion close, you can see that the arrows are getting bigger. So you see the arrows here got larger. And then you also see this point right here. This distance is this point that's been plotted. So what does that tell us? All right, so from what we were doing earlier, what happened to the electrostatic force when the distance between the two charges is increased? When the distance between the two charges was increased, the electrostatic force, so that was a force of attraction, also increased. The arrow size seemed to change. Let's go ahead and take a look back again at what happened. All right, so let's start back at 2.5. Let me see if I can get it to 2.5. Almost. Okay, so at 2.5, that's what our arrow size looks like, and the force of repulsion, once again, is 3.7. Now, if I go to 5, I'm going to actually go to 3.5, and then I'm going to go to 1.5. Just take a look at how big the arrows are. So if I go to 1.5, okay, now we're at 1 times 10 to the negative 8. Let's go back to 2.5. Okay, that's about there. And it's at 3.7. So we were, and then when I go to 3.5, then it's at 1.9. So the arrows seem to be getting bigger very quickly, and it gets small very slowly. So it's still small, 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 and then it gets bigger, and then all of a sudden it gets very large. So what's happening here? So we want to say that the arrow size seems to get larger very quickly, and it stays small for a much longer period of time, I guess. And instead of saying it stays small, we can say that the arrow size get larger very quickly when the distance was decreased, and small very slowly, or stays small, or decreased slowly when the distance was increased. Okay, so let's just move that over a little bit. Now what we're going to do is draw our evidence. Okay? We can probably make a table. We can draw some diagrams. Let's go ahead and make a table. And I'll just make it with using the writing tool. So we'll call this, there's distance, and then the FE. So let's go back to our screen. Alright, so let's take a snapshot of this. So 0.89 angstroms is our distance, and our force of repulsion is 2.9 times 10 to the negative 8th. Let's go write that down. Alright, and so now we're going to pick a different distance. Okay, so maybe we'll pick 1.65, and we'll use the force of repulsion at 8.5 times 10 to the negative 9. So let's go put that in our table. So I'm just writing our information here. Let's see. We had 1.65 angstroms and 8.5 times 10 to the negative 9. So times 8.5 times 10 to the negative 9. Let's just take a few more data points. So I'm just trying to make our graph here a little bit more data points. So we have another 1.22. We have 0.97. What happens when we go to 0.82 and 0.22, 0.93, 0.66. All right. And so what we see end up happening here actually is we start to see a curve. So there's a curve happening there in our graph. Alright, so I'm going to insert this curve that we see here on our graph and put it in our notes. So, let's see. Alright, and so we had a graph, and on our y-axis we had the electrostatic force, which they call the force of attraction. And then on our x-axis we had our distance using angstroms. Okay? And our force is always in newtons. And so we started to see a graph shape that looked like this. Now this is not linear. Okay, so there's a curve, and I'm just going to tell you what it is. It's an inverse. Okay. So to finish it off, we're going to go back to the one again. So the charge on the object with the force they feel. So charge is going to be, so when we change the charge, what happened to the FE? When we increased the charge, the FE also increased. When we decreased the charge, it also decreased. When we decreased the charge, the electrostatic force decreased. And so you would say that they're directly related. And I'm tired of writing charge over and over again, so we're going to call it what it is, which is Q. And charge over here is Q. So if I were to have FE on one side and Q on the other side, so this would mean that there's one that increases, the other one increases. But we forgot an important point. An important point here is that there are two objects. So both objects have a charge. So we need a charge 1 and a charge 2. Okay, so we're going to continue building on this. And so what we have is we have an electrostatic force, okay, which is we have Q1 and Q2. So remember that those two are charges. Now let's go back to this mathematical relationship. The distance between the charged object and the force. So what happened to the distance, or when we increase the distance, what happened to our electrostatic force? Well, we can see that when the numbers were going up in the distance, the force was going down. I don't actually think that I think that's a 9. So when we increased the distance, the electrostatic force decreased. When we decrease the distance, so if we go backwards, so if we're going, when we're decreasing it, what's happening to our force is that it gets bigger and bigger. So our force gets bigger when the distance, oh sorry, that's not what I meant to write. When the distance got smaller, the electrostatic force got larger. So that means that they must be on opposite sides of the fraction bar. So if we had Fe on this side, distance would be here, right? Because when the denominator is large, this overall number gets smaller. So we would assume that distance, whoops, that is very thick. Let's go ahead and erase that green line. So distance is at the bottom. And it didn't get bigger evenly, right? So I'm just going to tell you right now that it's a squared, and then also that there is a constant here. All right? And so this is our Coulomb's law equation. I'm just going to tell you that, oh, sorry about that, that K that we will use in class is 9 times 10 to the 9 newtons times meters squared over Coulomb squared. So the unit for charges, let me use a different color. The unit for the charges is Coulomb. And we use a capital C. The unit for distance, still meters. Okay, so meters, we were using angstroms. Okay, that's fine. And the unit for force, as we have been using all year, it will be newtons.